The last Docker session we discussed and we set the context at the beginning. Things we are going to explain, things we are explaining may not 100% accurate, because I wanted to set the context and the background for you. I remember one or two of you asked a certain questions. I told, okay, I'll explain that in the next session, because yeah, you went and did some research and then you figured out what we discussed and what the research says is different. Okay? That because we kind of kept as a story in a gray area. So today I'm going to dig into that and explain technically how exactly it works. So by nature it will be a little complicated. And here also there are part you to do the research, because there are certain concepts, especially when it comes to the OS level concept, explaining like this in a training, and then each one of you grabbing the way you think this is it. Okay, so when I say for example, last time I said Docker, it's just when you get it's just a kernel, right? So someone might understand kernel in a different way. If they understand the kernel as some sort of a package, they think this package is coming. If they understand the kernel as a process, they think like that. And also at some point I told image is when you give the Docker run, it become a container. When you stop, it become an image. Right? In reality, it doesn't become an image, it go back. Right? So that is what it is. So those type of things you will understand the way you think this is it. So likewise, today also when we explain certain things, you will understand according to you think this is what it is. So that is why I wanted you to work with your mentor closely, right, within the today, and then figure it out, the missing pieces, right, probably even you can sync up, and then you go from there. We had two competitors for this paradigm. One is the VM, another one is the containers, right? VM and the containers. So we discussed the history of this, where we had the physical servers, then physical server became the VM, and then VM went to the Dockers, and eventually we have something like a serverless. It is like, I remember someone commented, though it's a serverless, somewhere there is a metal box is running. True. Okay, so this was the evolution. The main difference between this we discussed, when it comes to the VM, this almost, right, this almost a machine, right? This almost a machine. This is not a machine, but this is almost a machine. What I mean almost a machine, it has its operating system, right? That means it has its own kernel, it has its own processors and so on and so. It is a machine. In container, in the last session we discussed, we are taking the what exactly needed from the OS. Okay? I told, when you taking from a container, when you say from Ubuntu, you take what is necessary to run the container. Okay? That doesn't mean in any manner you are cloning Ubuntu into your container. Okay? So we discussed, if you install Ubuntu, it takes 2 GB of space. But if you run the container, it's like a 35 megabytes or something like that. Sometimes even it's a 5 megabytes. So what we do here is, it is like we run as a process to the host operating system. Okay? For the host machine, it is a process. Okay? So we are going to discuss something called C groups and namespaces in a while. Then you will understand how this exactly works. So this is the main difference. You have a machine which has own operating system and own kernel spaces and everything, but containers, it is a process to the host operating system. So as a result, this use host kernel to it works. Okay, it used the host kernel to its work. Now we have a problem. Problem is, if your host is a Linux, if you running a container which says from Windows, mcr.microsoft something Windows, then you cannot share the host kernel. Why? Because it doesn't understand the Linux. Right? If you get the .NET framework, it supports Linux now, but if you get the operating system itself, it doesn't support. It cannot run on top of a Linux kernel. We are going to see it, why that happened and how it works. What you need to understand is container mean containers. Operating system see this as a other process. Operating system has no idea there is a container running on top of me. It acts as a process. Okay, so that is the main thing you need to understand. So now, as a result, what happened is this has a longer boot time. Right? This has a longer boot time. Why? It need to load the complete operating system. And this is very short, very short boot time. Why? Because it's just a matter of creating a process. It's a matter of creating a process. Okay. So usually in Linux we are going to discuss this. We have a process called fork and exec. Right? Fork has an extended version called clone. Right? So what it does is, we are going to discuss in a while how exactly this works. What the fork does is, it copy the existing process, right? And the exec is remapping the memory to the new program. So this happens usually in milliseconds. This happens in milliseconds, whereas it takes the full boot time. That is why containers are super fast, right? That's why containers are super fast. So, and third one, here you have hardware emulation. Where you do not have a hardware emulation because this is a process. Okay, that's the main three differences when it comes to the VM and the containers. Now, if you get the other, if you get this as in a real world, so VM is like you are building a house on your own land, right? You are building a house on your own land. You have a full control. However, containers, it's like an apartment. You're getting a room inside someone else's house. Right? You get a key and everything, but you don't have a full control. The house owner or the landlord will control you, but it is inside that, but you can use it, right? So if you get the VM, so you have the hardware, right? So on top of the hardware, you have virtualization software, something like, let's say, hypervisor. On top of this, you have a hypervisor, right? And then on top of that, you have a OS, and on top of this, we have your app. Whereas, when you come to the containers, you have the hardware, and then you have OS, and then you have Docker engine. We are going to learn in a while why you need the Docker engine, and then you have the Docker and the app. Inside the Docker, you have an app, right? So now you can see there is a very different. Here you don't see the OS. You only have the OS for the main hardware. So this guy going to share the kernel. So if you have two Dockers here, right? If you have two Dockers, then still both share the same OS kernel, right? That means your Docker don't have a OS. Your Docker don't have a OS. It doesn't contain OS. But you will see some MNT, SRC, all those OS file is there, user space, everything is there, which you are going to learn next how they do it. But you have it. You have it because when you say from Ubuntu, it take that file system, copy into your one. So you have, so that is why you have illusion that Docker has operating system. Docker don't have operating system. You see, one operating system. But here, if you create a other VM, right? So that also has a separate operating system. Got it? So though when you go Docker exec, last week we did, right? So then you go inside, when you say ls, you will see the file system. You feel like, okay, I have a separate different universe. No, you don't have it. You don't have it. Right? What you have is a template taken from the main file system. When you say from Ubuntu, from the Ubuntu, it take that one. But it doesn't have any sort of a kernel. All the thing you do inside this execute by the host operating system. We are going to see what's going to happen when you create the more processors inside this, what's going to happen. But everything what you do is done by the host operating system. Now this one I'll try to explain most possible simplest way. Okay, you must go and learn little bit detail about this, because I'm trying to explain this a way that most of you can understand. Okay, if you get the Linux, it's a two-stage of way of creating a new process. Okay, so it's some places it's referred as a copy and replace. Copy and replace. What it does is, when you want to create a process, it execute a command called fork. Not that executing a command, it says we fork the process. What the fork does is, it take a copy of parent process, right? Copy of parent process and putting into a new space. Okay, this doesn't mean it get the 100% copy of the parent process. What it means, there are certain things it's copying, right? So I'll explain what it copy and what not copy. So there are certain things it copy from the parent process and create a new one. It's like you're getting something from the template. So fork also, there is extended version of this called clone. Actually Docker use the clone, not the fork. I'll tell why when you discuss the namespaces, right? So now there is an exec process. What the exec does is, it replace this memory into the new program, the copied process memory into the new program. Let's say you have a P1 and running. Okay, when the P1, let's say P1's process ID is 1, 2, 3, 4, right? When you call the fork, it create a copy of a P1. The new process ID might be 1, 2, 3, 5, right? So that means just after the fork, the both will execute the same command. Why? Because it's a copy, right? It's a copy. So when it gets the exec, what happens is, this memory is pointing to the new program you're giving. Okay, That's why we learn in the Docker, if there is no active process, what happened? It killed. So now we did the copy, so that means the fork or the clone, and then we replace the memory, so that is the exec. Okay. Now what happens is, when you say docker run, right? So you give the command saying docker run. Right? So docker run. So docker run pass this message to docker d, which is a docker daemon. So through this, it's talking to the docker d. So docker d delegate this to container d, which is the container runtime. Right? Container d pass this to run, which is the very low level process to create processors. Right? So now this start the clone process. I told Docker use the clone, not the fork. Right? So now whose process it's copying? Whose process it's copying? When you give the run or clone command, it copy the parent process. Who is the parent? Runc. Right? Good. You copy runc. Why we use the clone? Right? When you use the clone, I don't exactly remember the name of those, you can pass arguments what you need to copy. Right? What you need as a copy. For example, PID, network, IO, right? So there are few things, I don't remember exactly, right? So it tells, okay, give me a copy of these from the current process. Right? So now it clone, now it's there. So under that, so every Docker run has a command, right? For example, you can say from, no, sorry, Docker run, this commands may not exactly correct, ubuntu latest echo hello. Now echo hello is the command. Right? So now what it does is, it get the bash, right? So this won't work exactly as it is. Huh? Get the bash and get that, copy that memory of that program memory into this newly created clone instance. So where you have Docker just boot. That is, this happens in the milliseconds, not like VM. Okay? This happens in the milliseconds. So you are copying but not replacing the memory. This is called COW, copy on write. Right? So what it means, the memory pages are not replaced until the exec run. Okay, copy on write. So you just copy and then the later on replace. So when you copy, I told only certain things will copy, right? So it copy task descriptors and it copy file descriptors, it copy memory pages, and it copy environment, right? So task descriptor, we are going to learn this in a while with the namespace and everything. So file descriptor, for example, when you create the Docker in the beginning, right, it get the std out and std error and everything from the parent, but with the exec, it replaces to your own spaces. If you get the environment, so this environment variables also replaced by the environment variable you are giving for the Docker. There are few others, just as a task, just Google and see when you give the copy on the Docker, not the give, Docker run, the copy, what are the attributes being copied. Obviously, this copy the namespace and the C groups. Namespace and the C groups, which we are going to discuss little in detail. There are, I think, 2 or 3 more. What happened when you fork? Right? Tell me, when you fork, what happened? It copy from parent, right? And it copy the struct, the memory I told as it is, and then what it does, it replace or it point to the new program binary, right? It point to the new program binary. So that is why this is called copy on write. If you get the exec, exec does not create a process. Why? Why? Exec does not create a process. Why? Exec execute followed by the fork or the clone, right? So what we discuss, see, the original process ID 1B 1234, but the new process ID might be 1235. Exec execute on the 1234 or 1235, 1235, right? So therefore, exec what it does is it throw away the all the memory pages what it has, why it is came from the previous struct, it came from the previous, right? So it throw it away and it replace from the new program binary. Okay, it's replaced from the new program binary. So that is why this two-stage processors is super fast, because you copy one and then another one come and do the thing. Okay, so it stays in the same PID. PID won't change after the exec, but PID change after the fork. Okay, when you debugging this is really important to see, figure it out whether it's creating new PIDs and everything is really important. So PID doesn't change followed by the exec. Okay, because exec doesn't change the PIDs, it just replaces. It's like you have envelope, you get the envelope and you throw out the existing letter and put the new letter and seal it, something like that. So now let's apply this to the Docker itself, right? Let's apply to the Docker itself. So when you give a Docker run command, we discuss, it's come to the Docker D, right? This may run on a PID 530. This is just arbitrary number, PID 530. So from Docker D, it hand over to the container D. It may be on a 531, right? From container D, it give it to the run C, right? This may be on a 532. What the run C does is, it do the fork and exec. So fork create new one. This obviously not the 532, it can be 533 or something else. After this one exec, we get some sort of a command, right, to execute. Let's say we get something like echo hello, right? So that process it start inside the container. Container's perspective, this is a PID 1. This is called isolation. Container's perspective, this is PID 1. The host perspective, this is 533. Host see multiple processes, but container only see one process. This is the isolation. Okay. Yeah, in the Docker perspective, yeah, good question. It's a clone. So is a Docker perspective, it's a PID 1. Container perspective, sorry, host perspective is a 533. So that means container see this one, whatever you do, as a new process, but with the namespace boundaries. You understand? The new process, namespace boundary. For the record, you went 10 years young, Jamsi, by having a haircut. This is again extension for the what we discussed the last session. So what is life cycle of a container? What learned that day, image with the run become a container and a stop become image. But I told it not exactly become image literally. What happens is when you give this, so this is an example Docker file. Docker from Ubuntu latest, run apt update and apt install curl and then copy app.js. What this does is it create layers, right? So you have file system template from Ubuntu. Okay. On top of that, it get the layer to all those curl and the app installed. And on top of this, it get the layer for the app.js, right? So every time it create a layer, these are immutable. Immutable mean you cannot modify, right? So now these are read only. Okay, but when the really Docker runs, when the image become a container, it adding one write layer. Right, this is writable. This is writable. That is why if you want to ping or something, we did the example, you go inside the Docker and we install the ping command or whatever the, if you need the Vim or something, you install it. That comes here. It's writable. So now what happens? The image became the container. Right? Give the run command. When you give the stop, it really does not become an image again, because image is already there. Image is a template. It doesn't really become that. But what happens is it is a stop container. Right? If I told that day, you get confused. What is a stop container and running container? Now you know stop container. However, this file is still there. The data you written still there, persisted. Okay, it's still there, it's persisted. If you start the Docker again, you will see all these modifications back. You will see all these modifications back. But if you give Docker remove, that time this file get deleted. That file get deleted. So every time you run, you get a fresh writable layer. Right? So if you have a database on a Docker, if you populate in some data, when the Docker starts, every time you run the Docker, you get this new data, unmodified data. You can modify the data on the runtime if you are not using the real physical volume, and then when the Docker remove, it's get deleted. So you Docker run image become a container, but stop really doesn't become an image. What happens is instead of that, it becomes a stop container. The stop container has this write layer. Okay, stop container has the write layer, the data you written. Okay, so some people, some places call this as a container layer, and different documents refer this in a different term. It's fine what it is. You just need to understand how this works. There is something called overlay file system, OverlayFS. So under the hood, Docker used this to merge all these and show you as a single unified file system. Okay, because it has a read layers and now it has a write layers. Under the hood, it used this OverlayFS to show this as a single unified file system.